Bonjour everybody, welcome back to another video and Happy New Year. Since there have been a lot of 2025 interesting little math things floating around on the good old internet, I snatched up one of them with my jellyfish net and I have now dragged it back to the table or tablet for you guys to witness the explanation of, I guess, which is not nearly as exciting as if I was eating it. This problem consists of multiple steps, and I will be basically leading you guys through all of them, like explaining them one by one, like each of the steps. So the first thing is 2025 is equivalent to 45 squared. You might say, alright, then just whip out the good old calculator. This is rather easy to determine. There is a little trick though, however, you guys might have heard it before from me or maybe from someone else, of how to solve the square if you're lazy or just short on time. Of a number that ends in 5, besides 5 itself, because the 5 itself doesn't count, it has to have something in front of it. So as you guys can see, 45 squared. What is 45 squared? Let's just say that if our first digit is n, and the last digit is 5, how do we solve n5, as in digits, not n multiplied by 5, squared? So we basically have said formula as follows: n multiplied by n plus 1, and then slap a 25 at the end. Like so. Not multiplication, just digits. So for example, in our case, it's 45, so slap a 4 into n's place instead, so we just have 4 multiplied by 5, which is 20. So then you just pop a 25 onto the end, and we get the year that we are currently living in, 2025. Whoop-de-doo. Okay, so now I'm going to be explaining the next part that is worth explaining. So basically this part. What is this part, first of all? So we're just randomly popped this. 5 times 9 is just simply 5 times 9, but the reason why they put it there has to be explained after this. Interesting order, of course, but it's fine. So 1 plus 2 plus 3 plus all the way up to 9 squared. That is equivalent to 45 squared. And it just so happens that this case scenario is rather easy to solve, but this introduces a little formula that if we just swap our maximum number instead of 9 as n, what are we gonna get? So this is a little tricky. So plus 3 plus ... This will be used a lot in the other problem as well, so let's just get rid of the parentheses, because it's just square, no square, just get rid of the square, whatever. Basically, when you first see this problem, if you don't know the formula, if you do know the formula, just bear with me for a second, but if you don't know the formula, what is your first instinct to solve? Of course, it's just to connect our little lines here, our little friends. So 9, 1, 8, 2, 7, 3, that's just pure elementary school instinct. But if you didn't know what the maximum number was, how would you do it? So basically, for this problem, we're going to use two cases. If n was odd and if n was even. I'm going to go for if n was odd first. Okay, I left that a little too close to each other. If n is odd. If n was odd, like our case 9 in this scenario, the first thing instinct would be to connect n with all of the other numbers and pair it together, right? So how many pairs are there? There are n minus 1, because n obviously does not divide perfectly if it is odd, divided by 2, multiplied by the equivalent of all the pairs. Since we are going from 1 to consecutively to n as the maximum number, all of the pairs are going to be equivalent to the maximum number plus the smallest number. So in this case, like 9 plus 1, 2 plus 8, so on, all of them are equivalent. So then this is multiplied by n plus 1, and then we have to add the middle number, the median, which has not yet been added, which is then equivalent to n plus 1 divided by 2. If we do a little bit of whoopsie-daisying here, and we pull out the n plus 1 into this equation, so if we have n plus 1, then we get, and we just combine them both together, this is n plus 1, n minus 1, plus, well, this is just reduced to atoms, it's just 1 now, divided by 2. So then this evens out, and now we basically just have n plus 1 multiplied by n, or in standard writing, n multiplied by n plus 1 divided by 2. Okie dokes. So that is if n is odd. If n was even, on the other hand, actually gives you a much easier thing to work with. Because similarly, like here in our 2-9 example, if we just smack a 10 onto the end, we're going to save ourselves a lot of steps. So basically, if even, yippee, this is equivalent to, with our smack 10 onto the end, since we can now divide cleanly, we do not need the n minus 1 step anymore. It's simply just n divided by 2. Just have n over 2. Still multiplied by n plus 1 though. N plus 1. But this time, that is basically all there is, because there is no middle number anymore, so we don't need to worry about that. So this step is a lot more simple. It's literally just n multiplied by n plus 1 divided by 2. So as you guys can see, if it was odd, if it was even, it makes no difference, because in the end, in the eyes of this formula at least, both of them are basically the same. So still n multiplied by n plus 1. So this is the really only fruit that we are bearing from this current long equation that I have just solved. So we're going to save this for the rest of this video. So let's just get rid of all of this and give us some scrap room. So now that we know that n multiplied by n plus 1 is our said formula, we can now return back to the second step of our original phase. Popping in the 9 to the n multiplied by n plus 1, we get 9 multiplied by 10 over 2. And obviously this simplifies out, getting you just 9 multiplied by 5. So now we know why 45 is equivalent to 9 multiplied by 5, but we have ended up popping open a much larger can of worms. Because this equation is also equivalent to this equation, as the problem already tells you. However, does this work? Since this works for any value of n, would it work for any value of n as well, any positive integer n? So we're going to be proving that in this video as well. So for any positive integer n, we have this equation. And why is that equation though? Because I'm here to explain it after all. We can use this with the starting numbers, basically on both sides. So just forget about all of the random stuff first, and just go from 1 squared is equivalent to, well, 1 cubed. And that's pretty easy to remember, so this is basically our first step. If we keep increasing, however, we find that the second step would then be equivalent to 1 plus 2 squared is equivalent to 1 cubed plus 2 cubed. And this is actually rather easy to solve because you just 3 squared, 9, and then so on, so on. However, does this work for any value of the maximum number? So currently the maximum number, for example, in the second one is equivalent to 2, and every time we keep adding a n to the third on each side of the equation, but does this work for any positive integer n? So that's what we were trying to prove right now. All the way down into the deep dark rabbit hole, we see that 1 plus 2 plus 3 plus all the way up plus n squared is equivalent to 1 cubed, 2 cubed, 3 cubed, all the way up to n cubed. But backtrack, because we can't prove this from just this equation alone. There is another way that we can do this. So moving back just one step, we get the equation 1 plus 2 plus 3 plus all the way up, this time only to n minus 1. So this is basically just 1 behind n. One step behind n, basically. 1 cubed plus 2 cubed plus 3 cubed plus ... plus n minus 1 cubed. And you might ask, Lon, this is stupid. Why are you doing this? And why are you backtracking instead of going forward? Well, the thing is, in both of these equations, since we're saying that they're equal currently, just try to see if they are, we don't actually know if they're equal or not yet. But basically, the only difference between these two equations is an n to the third. Because right before this is our n minus 1 to the third, right? So that means that on both sides, if these guys are remaining equal, since they started from the same start, 1 squared is equivalent to 1 cubed, what a humble beginning, Both of them are equivalent. They started from the same thing, and if they keep adding the same thing on, for any positive integer of n, will it stay the same? So that's basically what we're trying to prove right now. That means that if we use this to subtract this, just simplified of what I just said, will it be equivalent to this subtract this, which is then equivalent to n to the third? So this equation minus this equation has to be equivalent to n to the third for us to prove our point. Okay, so basically, if we do that using the same formula comes to save the day, this formula above, we have, for both equations, n multiplied by n plus 1. So this is our larger equation, the second one, squared, subtracted by, since this time it's n minus 1, so the n plus 1 is just going to be substituted for n. I'm going to write it in the same order, however, so just don't get confused. Wait, there we go. Divide by 2 squared. This has to be equivalent to, or so we hope, to n to the third, but right now we don't know yet. So we just have to solve this equation. Whoop-de-doo. That'll be fun. So basically, in case you guys don't know, there is a formula in which if we have the a and b, a minus b, a squared minus b squared, is equivalent to a plus b multiplied by a minus b, which is a rather commonly used formula. And we can pop that in this work as well. And you might say, but Lon, these have a bunch of different things in them, like fractions, and they have ends, and they have parentheses, but it basically works the same way. So if we basically distribute the parentheses and then apply the a and b to it, so let's just say this inside bit is a, this inside bit is b. So we basically have, just randomly scrolled up, n squared plus n, so that's that just distributed, and then plus b, so then plus n squared minus n over 2, and now the squares are gone, so we don't need to worry about them. And then this is the minus part, so then we have n squared plus n, still going the same way, until now, and then minus n squared plus n, because this time the outside the parentheses it is negative, so inside the parentheses it has to change. Like so. So now we just need to do a solving, and it might look menacing at first, but you can see that there are a lot of simplifications in this problem as well. So this n and this n simplify out, leaving you with just 2n squared over 2, multiplied by, and this n squared and this n squared even out, 2n over 2. Simplifying, we find that we just end up with n squared multiplied by n, getting you n to the third. Wow, that is literally just what we were looking for. How very coincidental, am I right? Anyways, so now we know that yes, it does work for any positive integer n. And just leaving this video on a more lighthearted and easier to solve note, we can basically try to determine what the next year that will also work this same property will be. Spoiler alert, we're not going to live to see it unless humans somehow find a way to be immortal. But basically, since 2025 is from 1 added to 9, we're just going to pop a 10 at the end. Then we're basically going to get 45. So since this is 45, you add 10, you get 55. So we basically have 55 squared. Using the same way that I taught at the very, very start of the video, we have 5 times 6, because 5 multiplied by 5 plus 1. 5 times 6, that's 30. Smack 25 at the end, we have 3025. So unless humans find a way to live 1,000 years, we're probably not going to go see that day. However, it's still an interesting thought to leave the video on. So yeah, that's the end of this video. Hope you guys enjoyed, and I'll see you guys on the next one. Happy New Year. Bye-bye.